Okay, let's unpack this. In our last deep dive, we started getting into transformers.
Yeah, the basics of it, the tech behind so many large language models today.
We talked about breaking text into tokens, those little pieces, and turning each one into, well, a number representation, and embedding,
Right, these high dimensional vectors. And we touched on how direction in that embedding space can actually mean something.
like the king to queen example. Add a vector, shift the meaning.
Exactly. But, and this is key, those first embeddings, they're kind of like a dictionary lookup, context free.
Right, so the embedding for, say, bank is identical if you're talking about a riverbank or a money bank.
Which is obviously not how language works. That's the problem the transformer has to fix.
It needs to take those basic generic embeddings and tweak them, refine them so they capture the meaning in that specific sentence.
Yeah, think about mole. Could be the animal, could be on your skin, could be, Avogadro's number in chemistry.
Totally different meanings.
Mhm.
The transformer's job is to figure out which mole by looking at the surrounding words.
Exactly. You want the mole in digging for a mole to end up with a different final vector than the mole in checking a mole for changes.
So the mission is to bake that context into the word's representation.
Precisely.
And the core mechanism, the engine that drives this context building is called attention.
Mm-hmm.
Now, got to say, attention can feel a little confusing, maybe a bit mind-bending when you first bump into it.
Oh, absolutely. It's not always immediately intuitive.
So if it takes a bit to sink in, that's totally normal.
Mm.
Our goal here, using this great video explanation as a guide, is to really walk through how it works. How attention lets a word, like, look at its neighbors and update itself based on what's relevant.
So, okay, we're starting with our sequence of words, each with its context-free embedding.
Yep, the lookup table versions.
And the fundamental idea is each word needs a way to sort of pull in information, gather it from other words in the sentence or sequence to become context aware.
And this is where that famous paper, Attention is All You Need, really changed the game, right? It proposed this mechanism for words to interact.
It really did. It provided this elegant way for them to share information dynamically.
So let's use an example from the source material. Something simple, like a fluffy blue creature.
Okay, and let's say we're focusing on the word creature. We want its embedding to absorb the meaning from fluffy and blue.
Right, so it understands what kind of creature we're talking about. But how does creature know to pay attention to fluffy and blue and maybe, like, ignore A?
Ah, that's the clever part. This is where the mechanism introduces three really important concepts for each word. For every token, it learns to generate a query, a key, and a value.
Query, key, value. Okay, 3 different vectors for each word.
Derived from the original embedding, yes. They're different learned transformations of that initial vector.
Okay, so take creature. Its embedding gets transformed into a query vector. What's the query doing, conceptually?
The query is kind of like the word asking a question. It's saying, here's the kind of information I'm looking for to refine my meaning.
So for creature, the query might learn to represent something like, I'm a noun, I need descriptive words nearby.
Sort of, yeah. It learns what profile of information is useful for updating itself. And then there's the key.
And the key is,
The key is what a word has to offer. It's like its advertisement. So for fluffy, its key vector might essentially say, hey, I'm an adjective. I provide descriptive texture information.
okay, so every word generates a query asking for info and a key advertising the info it has.
Exactly.
So how does the model match them up? How does creature's query find Fluffy's key?
It does a comparison. Specifically, it takes the query vector of one word, say creature, and compares it against the key vector of every other word, including itself, using a mathematical operation, usually the dot product.
A dot product, and that gives you a number, a score.
Yes, a score. A high score between creature's query and Fluffy's key means, hey, these two are highly relevant based on what the model has learned.
And presumably a low score between creature's query and, like, is key.
Precisely. Low score means low relevance. A doesn't offer the kind of description creature is looking for via its query.
So you end up with like a grid of scores, showing the relevance between every word pair.
You got it. A whole matrix of these query key dot product scores. This tells you the raw relevance.
But raw scores aren't quite weights yet, are they? You need proportions.
Yeah.
Like how much attention should creature pay to fluffy versus blue?
Exactly. You need to normalize these scores so they represent a distribution of attention. And that sounds like a job for
A
us.
softmax. We talked about that. It turns numbers into probabilities that add up to 1.
Bingo. You apply softmax to the scores that one word, like creature, has calculated against all other words' keys. This converts those raw relevance scores into attention weights.
So you get an attention pattern for creature. Maybe it shows like 40% weight on fluffy, 40% on blue, 10% on itself, and tiny weights on everything else.
Something like that, yeah. Those weights tell you where creature should focus its attention.
Okay, so each word figures out its attention weights. But wait, there's a complication, right?
Yeah.
If you're processing text sequentially, like predicting the next word,
Ah, good point. Yes. If it's a decoder model or just generally processing left to right, you can't let a word attend to words that come after it in the sequence. That would be cheating, looking ahead at the answer.
right, so you need to block that somehow.
You do. It's called masking. Before the softmax step, you essentially force the scores between a word's query and any future word's key to be 0, or technically negative infinity, which softmax turns into 0 weight.
So a word can only attend to itself and the words that came before it. Makes sense. You don't want forest influencing the meaning of creature if you haven't even gotten to forest yet.
Exactly. Prevents information leakage from the future. So, okay, we have our attention weights, properly masked if needed. How does creature actually use these weights to update its own embedding?
This must be where the third vector comes in the value.
It is. Just like query and key, each word's original embedding is also transformed into a value vector, using yet another learned transformation.
And the value vector represents.
Conceptually, it's the actual information or meaning contribution that the word wants to pass along if it gets attended to. So if fluffy gets a high attention weight from creature, its value vector holds the specific fluffiness information that should be incorporated.
Ah, okay, I think I'm seeing it. For creature, you take its calculated attention weights,
The ones from softmax, high for fluffy, and blue, low for others.
and you use those weights to do a weighted sum. You multiply each word's value vector by creature's attention weight for that word, and then add them all up.
That is exactly it. It's a weighted average of all the value vectors in the sequence, weighted by how much attention creature decided to pay to each word.
So the value vectors from fluffy and blue contribute a lot because their weights are high. The value from A contributes almost nothing because its weight is low.
Precisely. The result of this weighted sum is a single vector. It represents the aggregated information that creature gathered from the context, based on relevance.
And that resulting vector is then added back to the original context-free embedding of creature.
Yes, that's the update step. The original embedding plus this aggregated context vector equals the new contextually refined embedding for creature, one that hopefully now encodes the meaning of fluffy blue creature.
Wow. Okay, that's actually pretty neat. So every word is doing this whole dance simultaneously, sending out a query, advertising a key, calculating relevance scores, getting weights via softmax, and then grabbing a weighted mix of everyone else's values to update itself.
That's the essence of it. And this whole process, the query, key, value transformations, the scoring, softmax, the weighted sum of values, that entire pipeline is what we call a single attention head.
One head, meaning one way of looking at the context.
Exactly. One specific set of learned transformations defines one way the model has learned to find relationships and aggregate information.
But context is way more complex than just adjectives modifying nouns, right?
Oh, absolutely. Language is incredibly rich. You have grammatical relationships, subject-verb agreement, for instance.
Or pronoun resolution, Sarah left because she was tired, linking she back to Sarah.
Right. Or just associative meanings like doctor and hospital often appearing together, plus relationships that span much longer distances in the text.
And it seems unlikely that one single attention head, with its one set of QKV rules, could capture all those different kinds of relationships.
It can't, really. It might get good at one type of relationship, but struggle with others, which leads us to multi-hybrid attention.
Ah, okay, so instead of just one attention process?
You run many of them in parallel. Each one is an independent head.
So for every word, you don't just generate one query, one key, one value.
Yeah.
You generate, say, 8 or 12 or dozens of them. One set for each head.
Yes, exactly. Each head learns its own completely separate set of transformation matrices for creating queries, keys, and values from the input embeddings.
And each head learns a different strategy.
That's the idea. One head might specialize in capturing local grammatical structures. Another might learn to link related concepts across sentences. Another might focus on verb-object relationships. They learn different ways to probe and extract context.
So each head runs its own attention calculation scoring, softmax, weighted sum of its own values, and comes up with its own proposed update vector for each word.
Correct. For our creature example, head 1 produces an update vector based on its analysis, head 2 produces a different update vector based on its analysis, and so on for all the heads.
And then how do all those different updates get combined?
Usually, they are concatenated together first and then pass through one more linear transformation to get them back to the right dimension, essentially mixing the information from all heads. You can think of it loosely as summing up the insights from all the different perspectives.
Okay, so the final really context-rich embedding for a word is its original embedding plus this combined update that incorporates insights from potentially many different kinds of contextual relationships, all discovered in parallel by the different heads.
That's the power of multi-headed attention. It gives the model the capacity to simultaneously capture a diverse range of dependencies and nuances in the text.
And this whole thing, multi-headed attention calculation, doesn't just happen once, right? It's layered.
Correct. This is just one part of a transformer block. The output embeddings from this multi-headed attention layer, which are now context-aware, become the input embeddings for the next part of the block, and then often for the next layer of the transformer.
Layer upon layer.
Yes. The model stacks these blocks, so the embeddings get progressively refined, the outputs of layer 1 become the inputs for layer 2's attention mechanism, and so on.
Which means the model can build up increasingly complex and abstract understanding of the context.
Exactly. Relationships identified in early layers, maybe local ones, can inform the discovery of more complex, long-range dependencies in later layers. It allows for this hierarchical processing of context.
It really drives home the scale involved. We mentioned billions of parameters. A huge chunk of those must be just for learning all these different query, key, and value transformations for all the heads and all the layers.
A very significant chunk, yes. The source material mentions tens of billions in GPT-3 just for attention. And a key reason this is even feasible is that attention is highly parallelizable.
Meaning you can calculate the attention for many words and across many heads all at the same time.
Yes, especially on hardware like GPUs, you don't necessarily have to process word by word sequentially within the attention calculation itself, aside from masking. This parallel nature is crucial for training these huge models efficiently. Scale really matters here.
Okay, let's do a quick recap then. We started with the challenge, word embeddings that lack context.
Yep, the basic dictionary lookup problem.
And the solution is the attention mechanism, which lets words basically poll their neighbors, figure out who's relevant.
Using those learned query, key, and value vectors to mediate the interaction, calculate relevance, and decide what information to share.
Right. And then multi-headed attention lets the model do this in many different ways at once, capturing diverse kinds of relationships.
Running multiple attention processes in parallel, each learning a different perspective on context.
And finally, stacking these attention layers along with other components allows the embeddings to become incredibly nuanced and encode really complex, abstract meaning.
Getting refined layer by layer.
It's a fascinating approach.
Yeah.
So next time, we'll dig into those other components in the transformer block, particularly the feed-forward networks or MLPs.
Which, interestingly, account for even more parameters than the attention mechanism itself, and we'll touch on how these models are actually trained.
Looking forward to it. But maybe one last thought to leave you with, connecting back to those multiple heads and layers.
Okay.
If these big models, like the one in the source, have something like, say, 96 attention heads in each layer, and they have 96 layers.
Whoa, yeah, that's a lot of heads and layers.
Think about that. If each head learns a different kind of contextual relationship, and these build on each other across 96 layers, what kind of incredibly intricate, abstract, maybe even unexpected connections between words, potentially spanning huge stretches of text, are all those distinct attention mechanisms collectively finding and baking into those final embeddings?
That's quite a thought. What complex webs of meaning are being woven in there?
Exactly. Something to chew on until our next deep dive.